Welcome back to our next discussion in Chapter 7 on applications of integration, where we're going to take a look today at arc length and surface area. So in the previous videos, if you remember, we talked about areas of regions bounded by curves. We then proceeded to take those regions and revolve them about some sort of axis of rotation, generating a solid. And now we're going to take a little step back and talk now simply about just measuring the length of a curve in space. And while it may seem like a simpler question, it will still involve the techniques and tools of calculus that we've learned so far. And so we have a very simple question on the board. What is the length of this curve? Is what I'm going to ask. So we have some sort of function f of x, continuous, meaning no gaps, breaks, jumps, differentiable, so the derivative exists everywhere inside this interval. And we want to measure the length of the curve. Now, if you remember back to algebra, the only type of curve we actually can measure in space is the length of a straight line. Unfortunately, this is a curve, and unless we were able to somehow take these endpoints and stretch them out and make it straight, then we would have no way of measuring it. And so right now, my only tool available is an approximation. I could approximate the length of this curve from A to B by using a straight line. And so say we just took a ruler, started at A, went to B, and measured the length of the green line. And while that would give me an approximation, we could do better. And so we're going to employ our ideas of what we know from calculus to try to develop a way to get a better and better approximation. Think back how we developed definite integrals. Right? We approximated with rectangles, and then we put more and more rectangles underneath the curve. And eventually, once we put infinitely many rectangles, we were able to then get a definitive area, or definite integral we called it. And in the same way, we want to measure the arc length. So let's try and get better and better approximations. And so what I could do is, okay, well, the green line is an approximation. It's not that great. What I could do now is start to divide up this interval from A to B. Maybe I first, cut it in half. And then I find this point on the curve. I measure from here to here, and then there to there, giving me a better approximation. I could then maybe subdivide those intervals. And now talk about these points on the curve and measure the straight lines between these points, giving me an even better approximation of the length of this curve. And we get the idea now, because it's very much a similar story in calculus. What would be the best approximation? Well, that would require me to do this for infinitely many points underneath this curve. And so let's try to develop a way to calculate arc length using calculus. And so if we remember back to algebra, we have to remember, well, how do we measure the length of a straight line? How do I measure the distance between 2 points? And so I'm going to remind ourselves of the distance formula. So we have the distance between 2 points, remember, is the square root of the difference between the x coordinates squared, so we'll call that delta x squared, x2 minus x1, plus the change in the y coordinates squared, delta y. And so let's take our interval AB and subdivide it into n subintervals. And what is the length of each one of these subintervals? We'll call them delta x, whatever it happens to be. We'll make sure they're all evenly spaced, giving me a bunch of delta x sized subintervals along A to B. And so we'll give the names. We'll call this guy then x0. This guy will be x1, x2, x3, ... xn. That would be the last one. Dividing this into n subintervals. And so what would the distance formula then become in relation to this function? It would be the square root of the change in the x coordinates, which is fixed, delta x squared, plus delta x is a measurement now. And then the change in the y coordinates. Well, let's explain that in terms of the function. That would be f of x, say, give it some I subindice, because we don't want to limit ourselves to the first or second one, minus f of xi minus 1 squared. So that difference squared as I goes from 1 to n. That would be the length of all of these little tiny straight lines as we move along this curve. We have the change in the x-coordinate squared, which we call delta x. We kept that consistent. We then have the change in the y-coordinates. Well, in terms of this function, we have to take two consecutive y-coordinates. So when I is 1, it's f of x1 minus f of x0, right? That first difference. Then f of x2 minus f of x1. Then f of x3 minus f of x2. And dot, 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 all the way to n, because the last one would be f of xn minus f of xn minus 1, the one right before it. And this would give me the length of all of these really small straight lines that I'm using to approximate this curve for n subintervals. And so the arc length would then be approximately the sum of all of these distances. So the sum, as I goes from 1 to n, of all of these really small straight lines. Delta x squared plus a little more space here, f of xi minus f of xi minus 1, that difference is squared. And if we add up all of these straight line segments, we get an approximation. Notice approximation, I'm not saying equals. And then naturally, we would like to let n go off to infinity. That would give me the best approximation of the actual length of this curve. Now, if we want to use the ideas of calculus, we'd like to turn this into some sort of integral because we see some similarities between the way the sum looks, what we're going to need to do when we let n go off to infinity, and the definition of the definite integral. But remember, a definite integral comes from some sort of function for heights of rectangles times delta x times a base. That's where you get the f of x dx in your integration. Now that delta x that I have is trapped underneath this root, and I can't just factor it out because this does not have a delta x in it. And so what we'd like to be able to do is maybe somehow get a delta x in this term so that I can factor it out and get it in the form of a definite integral so that when I take the limit as n goes to infinity, we get something that we can calculate. And so to get that, I'm going to remind us of something that we learned in Calculus 1, which is what we call the mean value theorem. Mean value theorem. And it says that as long as your function is continuous and differentiable on your interval, which it is, that's good for us, then the mean value theorem, I'll draw a picture to remind us, tells us that if we look at some sort of interval, and I'll put it in the context of what we're dealing with, so xi minus 1 to xi, look at the outputs of the curve over this interval, it's the curve f of x. So f of xi minus 1, f of xi. And we measure the slope between the endpoints. That would have to do with something about the straight line connecting them. The mean value theorem guarantees you that there is some point, I'm going to call it xi star because he's special. There's some point xi star in this interval where the slope of the tangent line is equal to the slope between the endpoints. And so let's write that out. So that tells me the slope between the endpoints, which is the change in the y-coordinates, over the change in the x-coordinates. Now remember, we call those delta x. So that would be the slope between the endpoints in this interval, that blue line, the slope of the blue line. Mean value theorem guarantees you that there is some point in between these two values, we'll call it xi star, where the slope of the tangent line, or f prime of xi star, that is the slope of the tangent line at xi star, is equal to that slope. The slope of the green line, given by the derivative, is equal to the slope between the endpoints, given by this fraction. Why do I bring this up? Because now if I just take the mean value theorem statement and I multiply both sides by delta x, giving me a sort of differential, we get a relationship between the change in the y-coordinates and the derivative. Now we learned about this in Calc 1 when we talked about differentials. This was actually something that we wrote out and discussed. And so what I can do now is I can take this expression and replace the change in the y-coordinates here by something in terms of delta x, specifically the derivative at xi star. And that is why it's always important, right, when the setup, we need to be continuous and differentiable. I need to be able to take a derivative of this function on this region. And so I'm going to go back to that Arclength formula, And we're still approximately the arc length, but what I can do now is I'm going to do a substitution. I'm going to replace that second term here by this expression. F prime of xi star delta x squared. So I'm replacing that second difference of the y coordinates with this expression in terms of the derivative and delta x. Now that I've done that, what I have is a delta x squared in common. If I distribute the square to each term, they each have a delta x squared, which I can factor out. And then I can also take it out from underneath the root because the square root of delta x squared is just delta x. And so simplifying this expression, we can pull a delta x out from the root entirely. What's left here? Remember, this does not go away. When you factor it out, now we're left with just 1 plus. When I factor out the delta x squared here, we're left with f prime of xi star squared, right? It still needs to be squared. But now that delta x is outside of the root. Why do I care to do that? Because now this is exactly the form of a Riemann sum. I have the sum as I go from 1 to n, the quote-unquote heights or values of a function dependent on I, times a fixed base. And if I let n go off to infinity, which is now what I want to do to get the actual curve length, we will generate for ourselves a definite integral. So the last step now is to do a limit, which gives me now the definition of a definite integral. So what is this the definition of? This is the definite integral starting at a and ending at b, right? x0 was a and xn was b, so I go from start to n. What am I summing up? Well, the square root's still there, that's not going away. The 1 is still there, plus f prime of xi star. Now, we realize that as I put more and more intervals in this region, the distance between xi minus 1 and xi is getting smaller and smaller. Eventually, this distance is getting infinitesimally small. And so at some point, every x value between a and b becomes a special point xi star. So actually, this will be true for all x. F prime of x squared. And delta x, remember, is our fixed distance in the x direction, the subintervals that are now infinitesimally small. Rewrite that in the Latin letter now, dx. And we see we have generated a definite integral in order to measure the arc length, the length of a curve. And so this is the formula now that we will use to measure the length of a curve. So in the next video, we're going to use this formula, do some examples, and actually explicitly calculate out some arc lengths. Because of the root and the square underneath the root, we are going to be limited in the types of arc lengths we can calculate at this point because we haven't learned our techniques of integration. But after we learn techniques of integration in Chapter 8, we can come back and revisit this and answer a little more complicated versions of this problem. But in the next video, we will take this formula and put it into practice. All right, talk to you soon.